Welcome to the mystery of the maths trumpet. You see, approximately 6 years ago, a Reddit user wandered into the r/mathpicks subreddit, and to much fanfare, they revealed this picture of a maths trumpet. Sadly, they then got exactly 0 community engagement, and then they proceeded to delete their account. So, there you go. People do not like the trumpet. Now, I forget how I came across this. Look, I searched for a lot of weird maths on the internet. Let's not get judgy here. But I found it, and I realized you can click through, and that's not the only picture of the maths trumpet. They put a whole album up. We get different angles of the maths trumpet from the side. I mean, that's either front or back on. I don't care to know. And look at that. I mean, that's head on towards -x. And this just really... this stuck with me. I'm like, that's an amazing trumpet. Like, it's such a phenomenal object, but what on earth is it? What does it mean when it says the complex values of -2 to the x? Multiple lines. Something with fractional values. It's roots. Right, so, to recap, both a positive times a positive gives you a positive answer, and a negative times a negative still gives you a positive answer. There are 2 options when you want a positive answer from squaring something, which means when we're looking at the square root of 4, which I'm going to write the fractional way around, that's going to be a theme today. So it's just whatever the root is, 1 over that. You've got 2 ways you can square something and get back to +4. That answer is either -2 or 2. 2 different roots. And the positive one is the principal main root, but -2 is along for the ride. And sadly, because neither of these are negative, if we had -4 to the power of 1/2, that equals nothing. I'll write that down. Nothing. Things get interesting down here in cube root town, because if we have a positive times a positive times a positive, so I'm just going to put positive cubed, that's still positive, but negative cubed, a negative times a negative times a negative, we're back in negative town. I'm going to cheat this slightly. 4 was a number I just picked to make the square roots easier, so I'm going to make it an 8 to make the cube roots easier, because that means now that if we have 8 to the power of a third, that just equals 2. And if we have -8 to the power of a third, it equals -2. So we've still got 2 solutions, but instead of both of them being when it's a positive base, we've now got 1 of each. And this is the beginning of the unraveling of the mystery trumpet. It's involving fractional powers. Fractional powers represent roots, and roots can give us multiple solutions, hence multiple lines on the mystery trumpet. However, we need to take a much closer look at this spot here, because the mystery trumpet isn't using 4 or 8, it's using -2. And so we need to work out what's going on when we're taking a fractional power of a negative number. It's about to get complex. You may remember from my previous video about fractals, I showed this GeoGebra file where I can move the complex number z around, and it shows its square, z squared, move accordingly. And one of the fun things we noticed was, if you take z all the way around the unit circle, if you watch z squared, it does 2 laps. And that's because for the same z squared, there are 2 different points on the complex plane that will give it, which I can show better with this new GeoGebra file, also made by my friend Sam, where now I can move complex number z around and see both of its square roots. So before I was moving z1 and you were seeing the squared move, now it's the reverse. And you can see there's always 2 solutions, and they're always exactly opposite each other. So we no longer have the issue of there not being solutions. There's always 2 solutions when you take the square root of a complex number. And nicely, if I bring z down to be 4, you can see, watch, z1 and z2, the 2 roots perfectly align with 2 and -2. So of course it collapses down to the real case.
It's worth noting this is subtly different to the trumpet because we're only ever taking a square root, not different powers. But what I'm trying to say is if we take the square root of -2, you get 2 complex roots.
The question now, though, is what about other roots, cube roots, fourth power roots, etc.? And they all work, but for those, we have to explore a fun concept I love called the roots of unity. The roots of unity are the roots of 1. And you're thinking, but we don't want that. We want when we've got -2 to some kind of weird fractional power. Well, this is just the case of that's equivalent to -1 to whatever our weird fractional power is, multiplied by regular old 2 to the same real number. So this whole thing on the right, all of this is a perfectly normal, boring value. This is the bit that's going to be complex. And I know I'm talking about negative and that's blah, blah, blah. However, we can just look at regular. What happens if we take some, I'm going to draw a dotted line for, it's not exactly the same, but it will be in a moment. What if we've got 1 and we're taking some root, some 1 over n, representing the nth root of 1. First up, square root of 1. If we've got 1 to the power of a half, well, 1 times 1 is going to give us 1. In fact, that's going to be a reoccurring theme. On my complex plot here, 1 is always going to feature. Because you just multiply 1 over and over again, you always get back 1. However, as we saw before, there's the cheeky, the non-principal root over here, -1. Because -1 times -1, also 1. So square root of unity, 2 roots. What if we skip ahead, however, to the 4th root? Because I times I is -1, and -1 times -1 is 1. So 4, I to the 4, still 1. And actually, you can put in a negative I as well, and that still works. So the 4th root of unity has 4 roots, and would you believe it? If you join them up, they make a perfectly regular square. You're rightfully thinking, hang on, you skip right over cube roots. And that's because 4th roots are just so nice and neat and tidy because they end up on the axes, they give you the square. Cube roots, there are 3 of them. There's one down here, there's one up there. They're symmetric on -1/2, and that there is root 3 on 2i, and over here is -root 3 on 2i. Root 3, I've done a video all about how much I love root 3 on 2. The reason it's appeared again is, sure enough, these 3 roots form an exact equilateral triangle. Badly drawn. So this means for any 1 over n, any nth root of 1, you're going to get the regular n-gon of points, all the corners of which are a valid root of unity. We, however, want -2 to the x, where x is the value of 1 over n. Well, to get the negative version, if this was negative, it just flips the entire thing. So instead of starting always at 1 and then filling in the points, you start at -1 and then fill in all the points. That still works fine. And as we saw before, by multiplying by this real, we can get to -2 to the x. So what this means is our value of x up here, that's what equals, well, at some point it'll equal 1/2, it'll equal 1/3, it'll equal all of them, but it's actually going to vary continuously. I shouldn't be just drawing it as some list of values. It should be the real number line. And we can add that to the diagram badly by having it, here we go, it's now in 3D. There's our new axis for the value of x. And imagine that like coming out of the board towards you. And so these points that we have as the roots, as x changes, they're going to change values. They're going to move around. And so they will move and change as you come out in 3D. And that, my friends, is the mystery trumpet. Only we could visualize it in 3D. We can have a look at some of those roots using this, the -2 to the x Explorer. I'll start by just turning on the principal root k equals 0. And oh, look at that. Ah, I'm already in love. That's so cool. Look at that 3D spiral. So the lazy way to plot this would have been like end on. So if I just swing it around like that, what you're seeing here, you're looking at the complex plane, and as you vary x gradually up. The point moves around as the principal root moves around on the plane. But by utilizing the third dimension, so the third dimension now, that's the value of x as it changes. We get this fantastic 3D shape that shows you how the principal root changes. Now, one spirally thing like this does not a trumpet make. So let's chuck on k equals 1. We've now got 2 of them. Look, it's so great. And you can see it's a similar shape, slightly tighter coil. And the dots are because we're sampling it at discrete points. We can switch on k equals -1. Look at that, we're seeing all of the principal ones and the symmetric roots on either side of that as you go either way around the circle. Because you can either go all the way around a circle to cover it, or you can go half in each direction, and that's the way we've set this up. And as I turn on more and more of these different roots, you can see it fills in the mystery mass trumpet. Mystery no more! There it is. We have recreated it from scratch, and because this is a custom bit of code rendering it for us, I can zoom in. Look at that. I'm going to go right down the trumpet. Isn't that phenomenal? And if I turn around to look, can I look back up the trumpet? There we are, looking right up the trumpet. Why do I keep saying that? So you can see in here, this bit that close up looks like a cylinder. We zoom out, and that is the mass trumpet. I'm so pleased with this. This was built for me by someone named Zach. You've got to download the code. It runs as a local host. This is actually all happening in a browser. I'll make that code available if you want to check out Zach's incredible -2 to the x Explorer. And it can do so much more than I've shown you here. You can change the bass. It's great. It may seem obvious, but the reason it looks like a trumpet, or rather it looks like an object at all, is all the lines for the different roots are kind of confined to the one surface. And that is a trumpet-shaped surface, and I wanted to see the actual surface. So I 3D printed one out. This is the trumpet surface, and I've just put the single k equals 0 root on there in a different color filament. And I love, look at that, it's an actual little trumpet, and it actually, would you believe it, sounds like a trumpet. Ready? Pretty convincing, eh? The question that occurred to me once I printed this is we have a continuous line representing an ever-changing primary root. Speaking of 3D prints, this video is brought to you by Bambu Lab 3D printers. I'm Business Matt, and I have more to say about them, but there's no time now. Meet me at the whiteboard. I don't know if you noticed, but before, when regular Matt was doing all the maths on the whiteboard, behind it is the Bambu X1 printer. I love this thing so much. In fact, oops. I'm Business Matt, not Maths Matt. So it's a Milestone desktop 3D printer. This thing, it really changed the game. You can use it at home or at work or any level surface you can put it down on. It's extremely stable depending on how you put it down, and reliable. And you know what? Previous 3D printers, I didn't bother getting one because they took so much babysitting to make sure they got it right. This one, it just works. It's great. I am the enthusiast in the final point here because it is a top choice for studios like Professional Printing or enthusiasts. And you may know if you watch these, every time enough of you buy a Bambu Lab printer, link in the description, I get to do another one of these. People send me in things to print in the sponsor spot, and right now this is printing a tablet, a Babylonian tablet from around 3,500 years ago. And on my phone, I can see like the live view. I'll screen grab this and put it up on the screen. I can see the live view of what it's doing in there. I'll often leave the office and it will tell me if something goes wrong, or I can check in on what it looks like. I love it so much. Although I am going to pause that for now because we're gonna have to finish filming the rest of the video. Once it's done, there's someone called Chuck sent it in. I'll show it now. If that print works, it's gonna take a few more hours before it's done. First ever evidence of humans calculating the square root of 2. Normally I make like an interactive weird maths thing that someone sent in. This one was just so on brand, I wanted to print it. So everyone, please do check out Bambu Lab 3D printers. It's currently up until the 15th of July, their 3rd anniversary celebration. Never a better time to get into 3D printing. And if you haven't got your own chucks, people sending in models, you can check out MakerWorld. There's a whole range of models ready to go. Here's just the mass ones. Print them on your printer. Right, back to the video. Thanks, Business Matt. A worthwhile interruption. And if you do have your own 3D printer, I'll link to this file, also made by Zach, below. Now, what occurred to me looking at this is it's a continuous line going around the trumpet, and that represents a constantly changing fractional power of a negative number. And we looked at things like the square root or the cube roots, but how do you work out how many roots there are for all the infinitely many in-between values? Previously on the whiteboard, I pointed out x is not this discrete value, it's this continuous thing. So it kind of makes sense that we get a continuous line out the other side, but how many values we expect, slightly more subtle. Now, if you just square something, -2 squared, so in that case, x equals 2, I know I've double labeled it, single solution. When x equals, when we did the square root, a half, 2 solutions. When x equaled a third, so the cube root, 3 solutions. But what if we go nuts? What if x is something, I don't know, 1.7? How many solutions now? Well, unbelievably, would you believe? 10. Same as 1.3. It's because what we're actually doing here, that is working out the values for -2 to the power of 17 on 10. And the denominator, 10, number of solutions. In fact, 3, 3, 2, 2, and we could rewrite that as, 2 on 1, 1. So you turn it into a fraction, and whatever it is, the bottom bit is the number of solutions. I have to come clean here. There was a single comment, I don't know if you noticed this before, on the Reddit post, and that was from the user who showed us the trumpet and then deleted their account. In it, they point out they actually set x equals to some fraction m on n, and then they do a set of possible values for m and n. So they are actually only doing discrete values, which is why their trumpet has dots everywhere. When Zach put it together for me, we switched to using it as a continuous line. That's why ours looks a little bit nicer. The comment does also talk about how you can do this with logs and how the logs are not unique, and that's just what I've been kind of hand-waving my way through. You're welcome to look up more on that. The issue now, however, is, wait, the trumpet, they're continuous lines, but there's always changing numbers of solutions. Continuous lines, but a changing number of values. They overlap. Whenever there's a point with fewer roots, all the lines overlap. So there's fewer spots at that point in the cone. So you can see that on our fantastic interactive version. If I zoom in near the middle somewhere, you can see, actually if I get right here, see there? See how there's like a massive gap seemingly in the cone? That's the point that corresponds to 1. Because when you raise something to 1, there's only one value. There's no fractional part. There's no roots. That's it. Up here, 2. That's just squaring it. -2 squared only has one value. So you can see there's like a wedge missing from the trumpet and a single value where all the lines cross. It is slightly difficult to see in the interactive version. It takes a little while to drag it around to line it up. So just for fun, we thought we would print them out. Now, we couldn't get the curved trumpet shape, so this is just a linear cone, but you can still see all the lines and the points here where they cross. So, for example, here, that might be 1, so either 1 or -1. As we go all the way around here, see there's no other dots at all, and then it comes back in there. Now, here we're recreating the original trumpet by just sampling discrete points. Of course, Zach also made a continuous version. So then we will make the print files available if you want to check these out below. So this is just, filling in the continuous line. And again, you can see all the points where they bunch up when there's a single root, or sometimes there'll be a root opposite each other. We did put the seam there, which might be a little bit foolish, but you can tell on the original, this is the printout before we made them. Look at that. You can almost, it looks like there's almost a misprint, like there's a slightly faint line. It's not. That's just it's lining up with the real axis, and that's what gives us a very faint line. Isn't that amazing? What a trumpet! That's the mystery of the mass trumpet. Thanks for watching. Here's another mystery. How could you come and see me live on stage? Well, I'm going to be at the Edinburgh Festival Fringe. Oh, so many shows. Please come and see my new show, Getting Triggy with It. It's going to be a lot of fun. And then I'm on tour around the UK in the autumn. Come to one of the shows. If you go to one of the shows that's offering VIP tickets, that just means you can pay extra, show up early, see the sound check. I'll do a Q&A with you. I'll sign your calculators ahead of the show and take photos and all that, so you don't have to hang around afterwards. And the VIP money makes the tour more fun because we use that money to pay for like the hotels we stay in and food. And so if we sell more of those tickets, the whole crew has a nicer trip around the country. If you can't afford it, it's fine. I will also do a meet and greet after the show. Anyone can show up for free. It'd be amazing to see you all there. Oh, and I got one show coming up in New York. All the details are in the description. And that's it for me. Thank you for enjoying this ride to find the world's best maths party house.